Jai Hind all of you. I am Manish Kumar, Assistant Professor in Department of Computer Science and Engineering at Akgec Engineering College. So today my fifth complex topic is on spanning tree algorithms. So let me start with that topic. So today in my lecture I will cover the brief introduction. What is spanning tree? Why we use spanning tree? What is the purpose of using spanning tree? Its applications. I will discuss applications. I will discuss about the properties of a spanning tree. Properties of a spanning tree. Why we need to find out minimum spanning tree. What is the application of minimum spanning tree? What is the purpose of using minimum spanning tree? And the two important algorithms that were used to find minimum spanning tree. That is Kruskal's algorithm and Prime's algorithm. Okay, students. So let me start with the introduction. Spanning tree. So what we study here, we will study different types of graphs. We will study graph. So first of all, we should know what is graph. So we know that graph is defined as set of vertices and edges. So this is the equation. You will all remember this equation. G is equal to V comma E. So graph is defined as set of vertices and set of edges. Okay. So spanning tree is constructed from any given graph. Okay. So I have written here a spanning tree can be defined as a subgraph. Okay, of an undirected connected graph. Undirected means we categorize graph into several types. So one of the type is undirected, another is directed. So undirected means there is no direction to direct from which vertex to which vertex. We have to travel. No direction is there. So in the graph where no direction is there, that is called as undirected graph. And connected means connection is there. We can start from any one vertex and after traveling, we again reach to that vertex. So that graph is called as connected graph. Okay, students. So spanning tree is defined as a subgraph, number one. Secondly, in a spanning tree, it will include all the vertices. It includes all the vertices. Okay, along with the least possible number of edges. So it means that from here we will conclude that for a given graph, there are more than one spanning trees are possible. Okay. So if any vertex is missed, it is not a spanning tree. This keep in mind. If any vertex is missed, then it cannot be called as a spanning tree. Okay. It means that a spanning tree is a subset of the graph. It is a subgraph, so we can call it is a subset of a graph that does not have cycles. Cycle means, for example, in a given graph, for example, this is a graph. For example, in a graph, we have these four vertices and we have these four edges. Let me call it 1, 2, 3, 4. Okay. So if I have start traveling from this vertex 1 to 2, vertex 2 to 4, 2 to 4 to 3 and 3 to 1, then this is called a cycle is there. So what happens in a spanning tree? In a spanning tree, this cycle should not take place. Okay, but we need to include all the vertices. Okay. So another important point that we have to keep in mind: a spanning tree consists of n-1 edges. So if n-1 edges is there, then it means that no cycle will be there. So this is the required condition for a spanning tree. Okay. So next, the applications of spanning tree where we use this spanning tree. Spanning tree is used to find a minimum path to connect all the nodes of the graph. All the vertices are connected in such a manner no cycle should be formed. So it is used to find a minimum path. Okay. And some of the important applications, commonly used applications where this spanning tree can be used, for example, in cluster analysis for finding out the group of clusters, group of nodes to analyze to which group that nodes belong. That is called cluster analysis. Civil network planning in civil engineering, this spanning tree application can be utilized. Computer network routing protocol. For example, in finding out the network routing protocol, we will use this spanning tree. So as I have illustrated, for example, I can show you with the help of an example. A graph is given such that it has 4 vertices, 1, 2, 3 and 4. Okay. Now, how many spanning trees are possible? That I have already said कि no cycle should be there. So we can, this is number 1, first spanning tree. Okay, na? Secondly, we can connect these vertices such that no cycle should be there. This is second. 1, 2, 3, 4. This is third. Okay. And also it can be like this also. Number 4. So now you can see that for the given example, for example, I have taken this simple graph. So for this graph, we have these 4 subgraphs. As said in a definition, spanning tree is defined as a subgraph. So these 4 subgraphs, and these sub 4 graphs are following all the properties. Number 1, the important is that you have to keep in mind no cycle should be there. So we have visited all the vertices and says that no cycle is forming here. Okay, 1, 2, 3, 4. These are the 4 spanning tree which are possible, right? And you can see that we have given with 4 vertices. And how many edges are there? 1, 2, 3. So I have said that important is that n-1 edges are there. Here. Okay, spanning tree consists of n-1 edges. So we can see that for a given graph, these 4 types of spanning trees are possible. So we can say that for a given graph, a number of subgraphs are possible, that we call it a spanning tree. Okay, students. So this is an example. Now, properties of a spanning tree. So as we have seen that there can be more than one spanning tree. Number 1, first property is there for any connected graph. Okay. Number 2 is a spanning tree does not have any cycle. That also I haven't seen. A cycle, or we can say it as a loop. No loop should be there. That we have seen. A spanning tree is minimally connected. So removing one edge from the tree will make the graph disconnect. Okay, minimally connected. We have to visit all the vertices such that we can visit all the vertices. So it should be minimally connected. Okay. Number 4, a spanning tree is maximally acyclic. But no cycle should be produced. So adding one edge to the tree will create a loop. So we have seen that when we add a one edge here, the loop will be completed. So we do not want to create a loop here. So this is a property maximally acyclic. Okay. Number 5 is that there can be maximum n⁻n-2 numbers of spanning tree. Okay. Tree that can be created from a complete graph. So this is a formula that you can remember. For example, we have n-2 numbers of spanning tree are possible. We can keep the value here and find out how many spanning trees are possible for a given graph. Okay, a spanning tree has n-1 edges that we have seen already in the property, where n is the number of nodes. Okay, students. So now next is minimum spanning tree. So what happened? Now we have created a number of subgraphs. Now what we need to find out of those subgraphs, we have to find out the minimum spanning tree. So on what basis we can find out the minimum spanning tree? On what basis? The basis is that, for example, I just give the weight of the particular edges. Let me give the weight 2, 1, 3, 5. So I have given the weight of this in this given graph. So for this spanning tree, 1, 2, 5. These are the weight of these edges. Here it is 1, 3, 5. Here it is 2, 1, 3. Right? And here it is 2, 5, 3. So let me calculate the minimum cost for this spanning tree. 5 plus 2, 7, 7 plus 1, 8. So the cost of this is equal to 5 plus 2, 7 plus 1, 8. Right? Cost for this spanning tree is 5 plus 3, 8. 8 plus 1, 9. The cost of this is 9. The cost of this spanning tree is 3 plus 2, 5, 5 plus 1, 6. Cost of this spanning tree, 5 plus 3, 8, 8 plus 2, 10. So we will find out ki the spanning tree which is having minimum cost. So the cost is 8, cost is here 9, 6 and 10. So we have seen ki this third spanning tree for a given graph having a minimum cost. So this is minimum spanning tree. So why we need to find this minimum spanning tree? Minimum spanning tree is find out, for example, let me consider these vertices as the cities. So we have to visit these cities in such a manner the distance should be minimum. So what we have done, we have find out the minimum cost. 2 plus 1, 3, 3 plus 3 is 6. So we will consider this subgraph. This subgraph spanning tree is called as minimum spanning tree, MST. Okay? I hope this is clear with this help of the example. So what is minimum spanning tree? A minimum spanning tree can be defined as a spanning tree, as we have seen, a spanning tree in which the sum of the weights of the edges is minimum, right? That I have illustrated. So the weight of the minimum, that weight of the spanning tree is the sum of the weights given to the edges of the spanning tree. So what I have done, I have added all the weights of the given, all the weights of the edges to find out the which spanning tree is minimum. Okay. So third is, in real world, this weight can be considered as a distance. For example, I have said ki, for example, I considered these vertices as the cities. Now I have to travel all the 4 cities in such a manner the weight should be minimum. The distance should be minimum. So I need to find minimum spanning tree. Okay. So in real world, we will consider that as a distance, can be considered as a traffic load, congestion or any random value. Right. So this is the application of the minimum spanning tree. Now we can use it in designing the water supply network. We can use this designing the telecommunication network. We can use in designing the electrical grids. This minimum spanning tree. Okay. And most importantly, it can also be used to find the paths in the map. Okay, students. Now, so I have already illustrated. Now you can see with the help of this example. For example, I have taken these 4 vertices A, B, C, D. It can be weights are given 6, 5, 2, 3. So 1, 2, 3, 4. These are the 4 possibilities. These are the 4 minimum spanning trees. Okay. So as I have illustrated already in the diagram, so I need to calculate the weight. So the sum 6 plus 5, 11, 11 plus 3, 14. So the cost of this minimum spanning tree is 14. This is a minimum spanning tree 1. Minimum spanning tree cost is 11, 13 and 10. Okay. So these are the 4 possibilities. So I will consider a spanning tree which is having minimum cost. So this is the minimum spanning tree we will consider. Now the problem arises how I can find which of the given subgraph having a minimum distance, a minimum spanning tree. How we find out? So in minimum spanning tree, to find out minimum spanning tree, we have 2 important algorithms. That is Kruskal algorithm and number 2 is Prime's algorithm. These are the 2 important algorithms with which help we will find the minimum spanning tree. Okay. So both Kruskal and Prime's have given their own approaches to find out the minimum spanning tree. So let me elaborate. First, number 1 is Kruskal. So as I have already stated, it is used to find the minimum spanning tree for a connected weighted graph. Connected means all the vertices are connected with each other. I can travel from any one vertex to any of the other vertex. Okay. Secondly, this algorithm will follow the greedy approach. Greedy means on the basis we will follow that edge which is having minimum cost. That is some greedy approach, that we call it greedy approach, which will find an optimum solution at every stage. Here you just keep in mind that at every stage we need to find the optimum solution. Optimum solution means at every stage you will find out now which edge is having a minimum cost. Okay. So I will show you with the help of example. Not globally, we will find out just focusing on global optimum, find out the optimum solution at every stage. At every stage we will find out. Okay. So let me fastly just review this algorithm, Kruskal algorithm, that is I have taken from Google by Googling the website. Kruskal algorithm. The name of the algorithm is Kruskal. So firstly, what we have initialized a set. A set. As we know that graph is defined as a set. So firstly, I have initialized a set in which initialize and as in empty set. I have initialized an empty set t is equal to 5. So for each vertex, because what we have to do, we know that edges for any vertex, if there any path exists from u to v, if there is a path from u to v, then that edge is completed. We can travel from one vertex to another vertex. So for each vertex v that is belonging to the vertex of my graph, what we will do, we will just make a set of v. ठीक है ना? Making the set u to v, number of edges are there. Now what we will do now we will sort these edges by increasing edge weight. Okay, so for easy solution, we will just make a table, and we will make a table in such a manner. We will write the edges here and weight. We will make for solving a numerical, we will make a table, and we will arrange in such a manner in increasing order. We will arrange these edges. So sort by E by increasing edge weight W for each u to v. U to v means edge is completed. U to v that belongs to E in sorted order. Okay. If that u is not equal to find set, these are the operations. This is the make set operation. Another is find set operation. Find set u is not equal to find set v. It means that edge is not already in the set. Then we have to travel that edge. Okay. So we will perform an operation. Union operation is performed. Means one by one we will add a new edge into our set by performing a union operation. Find set u and find set v. So this is a simple algorithm. So this is a illustration. So for example, this is my initial graph given here. So what we will do, I just firstly I will arrange the edges of this graph in a table. In a table. Let me make a table here. For example, the minimum is A, B, C, D, E. So D to E. We have traveled from D to E. This edge is there and having minimum weight 1. So I put it at number 1. Okay. First. Then secondly, A to B. I will consider this edge having weight 2. A to B. Okay. Then this is 3. B, E. In lexicographic order, we will visit B, E. Okay. 3. Now 4. A, E. A, comma, E. This is weight is 4. Okay. Then 5. C, E. C, E. 5. Okay. Then 6. B to C. Edge is there. Weight is 6. Okay. Then C to D. Sorry. C to D. Okay. C to D. Weight is 7. So in this fashion, you can arrange the edges. Now, what I have to do, I have to keep in mind, cycle should not be there in this. If cycle is not there, then we will consider that edge into our subgraph, otherwise not. Okay. So DE. So first DE. DE. Okay. So I have start. Number 1. I have considered this. Yes, right. AB. Can I take it? Yes, no cycle is there. I can take it. AB. BE. 3. BE. No cycle is forming. BE. Yes. Okay. AE. AE. Now students, we will not include this edge in our subgraph because when I include this cycle will be completed. So I will not include this edge here. I will make a cross here. Now CE. CE. Can I take? Yes, we can take it. No cycle is forming here. Okay. BC. 6. Again, I will not include this BC because cycle will form here. So not include this BC. Now CD. Again, I will not include this CD because cycle is formed here. So this is the required minimum span. So what we will do, I just add the weight 1 plus 5 plus 3 plus 2. 1 plus 5 plus 3 plus 2. 5 plus 1, 6. 3, 9. 9 plus 2, 11. So this is the minimum cost for this given graph. So see, I haven't seen the solution, है ना? And we are getting the same solution here. So now I can, I think that you all understand ki how to solve a given example. Any graph is given, you just firstly make that table here and just keep a track whether cycle is forming or not. If cycle is not there, then include that edge, otherwise neglect it. Okay, so this is Kruskal's algorithm, Kruskal's approach of solving, finding out the minimum spanning tree. Okay, now comes the Prime's algorithm, second. So this is again what approach we will follow here, greedy approach. Okay, and we will start with empty spanning tree. Okay, now algorithm find the subset of edges that includes every vertex of the graph such that some of the weights of the edges can be minimized. Okay, now let us see the algorithm firstly. G stands for graph, W for weight, R for root. Root means from which vertex I have started traveling. This is R. So for each U, initial vertex which belongs to vertex of my graph. Okay, firstly I will put a U, key value of that U as infinity. Infinity means I haven't traveled any vertex. So firstly we will initialize the root element. Then I assume that from that root element all the vertices are at infinity distance. Okay, so I will initialize the key value of all these vertices that I am going to travel as infinity. And U dot pi is the parent value. So initially what happened from the vertex from where we are start is that is a starting position. No parent is there for that vertex, so put it as nil. Okay, and the key value of that root element will be 0. So we will initialize the key value of root element as 0 and all the values of the vertices as infinity. Okay, now again initialize a queue, a set, put G dot graph, all the vertices of the graph should be put there in a queue unless that queue becomes empty. What we will do, how that queue will become empty? We will extract minimum. We will extract the minimum value from that queue such that V belongs to my adjacent vertex of the graph. For example, the same U belongs to V. So U and V, the path is there, and this is U and this is V. So this V vertex is adjacent to this U. So V belongs to the vertex of the graph which is adjacent. Okay, if V is already in Q and weight of UV is less than V, key value of V, then what we will do, we will initialize that U as a parent. For example, when I travel from this vertex to this vertex, I have reached to this vertex. Now this U will become the parent of this vertex V. Okay, so this is done here, and we will update the value of that V as weight of that U and V. That is given here. Okay, so this is MST algorithm. Let me illustrate it with the help of a graph. So this is a graph A, B, C, D, E. So what I just illustrate with the help of an example. Now what I have to do, just in an algorithm, I am starting from this A. So I initialize the value of this A as 0 and put infinity in all these vertices. Infinity represents that I haven't traveled these vertices yet, but the initial point is 0. Now let me show you with the help of an example. So for an easy illustration, I just make the table here. So A, B, C, D, E, F. So I have initialized value 0, this A, and put infinity here. Now I am starting from this A. So I am starting from this A. Okay. Now from A I can go to B to C. So A to B the path weight is 4. A to C the path is V, this 5. Okay. So in which direction we have to proceed? Having minimum value. So I have visited this A to B. I will include this is the part of my spanning tree, this edges. Okay, in this now I am at which? I am at B. Now I reach to B. Okay. Now from B there are three options that I can explore: B to D. B to D. Now this I have already visited. B to D. The weight is 9. I write it here 9. B to D. Okay. B to C. The weight is 11. Already we have minimum 5. So we will not write 5. We will not write 11 here. We will write 5 because we are having already a better option here. So we will not go from B to C. Now B to E. Yes, 7. Okay. Infinity is there. Now now we have to proceed in which direction? We are at B. We are at B na. So we have to proceed in which direction? Having minimum weight. Minimum weight C. So how when this 5 path is taken place? This is from B to C. This is from we have traveled from A to C. So this is the minimum. So we will consider this edge in our minimum spanning tree. Okay. Now we will now we are standing at C. So let me, for my remembering, I will put here C here. Now from C I can travel to B is already visited. Okay, na? Now C to E. Weight is 3 minimum. Already 7 is there, but we are getting a minimum weight. So I will write here 3. Okay, there is only one option. See, 4 is already there, 5 is already there, 9 infinity. So which is minimum? 3. It means from C to E. I will travel from C to E. Okay, students. Now I will at E. I am standing at E. I am standing at E. So this matrix will represent this particular column will represent the these rows will represent the Q. Okay. Now I am standing at E. So E, say we can travel to B. B is already visited. We can travel to D. D. So from E to D it is taking 13, but we have already minimum path 9. So we need not to write 13 here. E to F 6. So I will write here 6. Okay. So 4, 5, 9, 3 is already written. Now in which direction we will move? Minimum weight. So minimum weight is 6. Means E to, we can travel E to F in such a manner. Okay. Now I am standing at F. Okay. Standing at F. So from F I can go to D. Minimum path is there. Yes. Now I can write 2 here because we are getting a minimum option. So I have write 2. No other way to go, and which is also shown here. We have already visited all the vertices. Now the minimum is F to D. So we will travel here. Okay, students. Now we have seen that. Now we get the minimum spanning tree. A to B, A to C, A to E, E to F, and then D. 4, 5, 3, 6, D. So you can see that we have visited all the vertices. So we can find out the minimum cost. 4 plus 5 plus 3 plus 6 plus 2 equal to 5 plus 4, 9. 9 plus 3, 12. 12 plus 6, 18. 18 plus 2, 20. So this is the minimum cost for this given spanning tree using Prime's algorithm. So you can solve this Prime algorithm with the help of by tracking the value in a matrix, in such a matrix. So because this full row this shows the priority queue. So from this priority queue, which edge is coming out? The edge having minimum weight is coming out. Okay, students. So this is the illustration of minimum spanning tree. I hope in today's lecture you all get the concept of spanning tree, why we use minimum spanning tree, its application, its properties, and there are 2 important algorithms, Primes and Kruskal, that I have shown you with the help of illustration. Okay. So thank you.